Let's study effectively with Miss ICT Skill Builder.
Imagine you have a robot and you want it to do 5 jumping jacks. You could write out an instruction that says jump, hand it to the robot, wait for it to finish, and then hand it another identical instruction that says jump 5 separate times. It works, but it's incredibly tedious. In programming, we have a shortcut designed to avoid typing out the same instructions over and over again. We call it iteration. Iteration works a lot like a personal trainer. A trainer doesn't yell jump 5 separate times. They just say, do 5 reps. Programmers do the exact same thing by packaging their instructions into a single loop. But whether you're a human at the gym or a computer running code, you face the exact same problem. How do you know when it's time to stop jumping? You have to have a way to count the repetitions. Computers require a built-in mechanism to keep track of that count. Once they have that, they can automate boring, repetitive tasks indefinitely without needing us to constantly hold their hand. When we give a computer a specific number of repetitions to complete, we are building what is called a count-controlled loop. Every count-controlled loop needs 3 ingredients. First, a counter variable, a digital scoreboard tracking the current repetition. Second, start and end values tell the scoreboard where to begin and stop. Finally, the increment adds exactly 1 to the counter after every repetition, ticking it up. A count-controlled loop cannot function without all 3 of these ingredients. The computer requires absolute, unambiguous mathematical rules so it can operate predictably every single time. This pseudocode diagram shows the structure of a for loop. The top for command establishes the counter's start and end boundaries. Underneath, indented text defines the repeating action. Finally, end for triggers the increment, adding 1, and bounces the program back to the top. If a programmer forgets to include that increment or sets an unreachable end condition, the loop will never stop. In this infinite loop, the computer will just keep running that one repetitive instruction over and over, essentially locking up the program. An infinite loop will eventually crash the program. That makes the increment and the end condition the essential safety brakes for any repetitive code you write. This flowchart maps how a computer thinks through a loop. At the top, we set our counter to 0. Flowcharts don't have a dedicated loop symbol. Instead, they use a condition check and arrows, creating a literal circle back upward to force repetition. Looking at this diamond shape, we see the end condition framed as a true or false question, determining if the loop stops. Unlike pseudocode, a flowchart requires drawing the increment as its own distinct mathematical box before the arrow circles back up. Whether you write the steps out in pseudocode or draw them visually in a flowchart, the underlying logic of checking a counter against an end goal remains exactly the same. This pseudocode block presents a final challenge. Let's trace the loop shown here, asking the computer to count from 10 to 15. Walking through the trace, we see the loop output the first numbers in the sequence, 10, 11, and so on. Try counting this on your fingers. If our start value is 10 and our end value is 15, how many total loops does the computer run? The answer is 6 times, not 5. Because the loop counts 10, 11, 12, 13, 14, and 15, understanding whether those start and end values are included in the count is a critical skill. Now that you understand count-controlled loops, you can get a computer to perform thousands of repetitive tasks instantly without making a single mistake.
Thanks for watching. If this helped you clear up the concept, hit that like button and share it with a friend who might be struggling with it too. Let's build those skills together.